Welcome to this lecture. Today we will dive deep into an important topic in operating systems. The topic is Banker's algorithm for deadlock avoidance. We know that when we switch on the computer, the operating system loads into the main memory and it starts running. Then you will say that your system is booted up. The operating system runs in an infinite loop, waiting for processes to be created and executed in the computer. The operating system is waiting for you, the user, to execute processes. It is waiting for you to to open the Google Chrome. Maybe it is waiting for you to open Microsoft PowerPoint. The operating system is continuously waiting for users to execute processes. When you double click on any application, maybe a movie, a new process is getting created. This process can go through different states. So, for a process to get executed in the system, it requires some resources. The resources can be anything like memory, processor, printer, scanner, anything. When the process gets enough resource, it executes and it leaves the system by releasing the resources it was using. This is happening in your computer. So we know that the operating system is responsible for controlling, coordinating and managing everything in the computer system. It is responsible for managing the processes. It is responsible for managing the resources. It is responsible for managing the memory, secondary storage, protection and security and so on. Even though we are not directly seeing the duties of the operating system, being a user, it is actually anything and everything that helps you to uh, do operations on the actual hardware. The computer is just an electronic device. It has hardwares. To add two numbers, we have the adder. Adder is a logic circuit. But to add two numbers, we are just giving input of two numbers and getting the output very easily through the graphical user interface provided by the operating system. So you can say that the operating system works as an interface between we the user and the electronic device, the hardware. So we have already said that the operating system is continuously waiting in an infinite loop for processes and it allocates the resources. So you have to keep the word resource. It can be the memory, the processor, a printer, scanner or anything the process needs to get executed. We know that in our computer, the memory, the size of the memory is fixed. In my computer, the size of the memory is 8 GB. It is fixed resource. So if I have multiple processes which requires more than 8 GB, I will not be able to allocate them all at once. So the operating system must wisely allocate resources. Otherwise what happens? Yes, otherwise there will be some problem like a deadlock. In a deadlock situation, your system will hang because the processes at that time instant will not be able to move further. Then your system will get stuck. So clearly this deadlock situation must be avoided. We have many methods to avoid deadlock. The different methods to avoid deadlock are deadlock prevention, deadlock avoidance. Oh, sorry, the different methods to handle deadlock. Okay, there are different methods to handle deadlocks like deadlock avoidance, deadlock prevention, deadlock detection and recovery, and there is a fifth method called deadlock ignorance. So, in this video, we are focusing on the banker's algorithm for deadlock avoidance. In the banker's algorithm, it works effectively on systems where we have multiple copies of every resource type. So let us take an example. Assume that the entire running of your operating system from 8 a.m. to 8 p.m. is a video, like a video. Processes are coming into the system, they are taking their resources, consuming the resources and getting executed completely. They leaves the system, new processes arrives. Like that, the system is working. At a particular time instant t, maybe at 12 p.m., we are taking a screenshot of this video. That tells you different information. At the particular time instant t, which all processes are there in the system, which all resources are there in the system, how many copies of each resource is free to allocate. So these all informations are available to us at a particular time instant t, and we will call that a particular snapshot. So let us assume that in the present snapshot we have 5 processes: P0, P1, P2, P3 and P4. And we have 4 resource types: A, B, C and D. These resource type can be anything the process needs to execute. It can be processor, memory, hardware, anything. So these resource types have multiple copies. So we will have multiple copies of each resource types. Maybe we have 3 printers, 4 CPUs, 4 memory, 4 processors, like that, any number. So in the banker's algorithm, we will use a matrix called max. So this is the max matrix. What is the purpose of the max matrix? When a process is created in the system, it will inform the operating system what is the maximum resource requirement of that process. So this matrix tells you for P0, the maximum resource requirement is 0 instance of resource type A, 0 instance of resource type B, 1 instance means a copy of resource type C, 2 instance of resource type D. Now for P1, it requires maximum of 1 instance of resource type A, 7 instance of resource type B, 5 instance of C and 0 instance of resource type T. Like that for P2, P3 and P4. So when the process is created, the operating system is told, I need these much resources to execute. That is my maximum requirement. So simply the operating system will not allocate more than that. It is not required. So when the process is entering in the system or created in the system, it tells what is the maximum requirement of each resource. Now there is another matrix called allocation. So this matrix tells us what is the current state of allocation to each process. How much instances of resource type A is allocated to P0? How many instances of resource type B is allocated to P0? Like that. So here, this is our allocation matrix. At particular time instant T, 0 instance of resource type A is allocated to P0, 0 instance of resource type B is allocated to P0, one instance of resource type C is allocated to P0 and two instances of resource type D is allocated to P0. Like that for P1. The allocation is for A, B, C and D resource types 1, 0, 0, 0 is the instances currently allocated to processor P1, process P1. Which means process P1 is now holding one instance of resource type A, 0 copy of resource type B, 0 copy of resource type C and 0 copy of resource type D. For allocation of P2, P2 is currently holding one instance of resource type A, 3 instances of resource type B, 5 instances of resource type C and 4 instances of resource type D. For P3 and P4, we have to understand in the same way. How many copies of each resource type is presently with that particular process? Now, we have another vector called available. It tells you in this system how many instances of each resource type is free for further allocation. So this value tells you how many instances of each resource type is now free or available for allocating to processes. So this is a snapshot of your system at time t. So coming to the banker's algorithm, it has two phases. In one phase, the algorithm is checking whether this snapshot is safe. By the word safe, we mean that a deadlock is not foreseen. A deadlock will not happen. Okay. Unsafe means that a deadlock may happen. That is the difference between safe and unsafe. A system is safe means that at a particular time instant t, we know what all processes are there, how many resource types are there, what are the current values of allocation for each process, how many resource types are free in the system. Using these values, you have to check whether this system will go to a deadlock. If the system will go to a deadlock, we say that the system is not safe. If the system will not go to a deadlock, we will say that the system is safe. Now, how do we understand whether that there will be a deadlock or not? So, safe means that the state is safe if all the processes at this time instant can execute in some order. The order of execution doesn't matter, but all the processes at that given instant must execute in some order. Everyone should be able to execute. Then, unsafe means that at least one process will not be able to execute. So the system is waiting without going forward. That condition is called a deadlock. So in this system we have n processes and m resource type. And each resource type has k instances. So the first phase of Banger's algorithm is to check whether the system is in a safe state. And the second phase of the Banger's algorithm is known as a resource request algorithm. In that phase, the Banger's algorithm will see a process asking for resources. When a process asks for resources, the operating system should decide whether to give resources to him or not. When will the operating system give resources? Yes, if the system will be in a safe state after giving resources. Otherwise, the operating system will tell that process to wait. So in that phase, the resource request algorithm, one process will be asking for resources to the operating system. The operating system will pretend like the resources are granted. Now that will make the necessary changes, like it pretends to have granted resources to that process. It will make changes in that this snapshot. Then you will get a new state after allocating that resources to that process. In that state, we will have to check for safety. We will have to verify that state will be safe. If that new state is safe, we will grant the resource. Otherwise, we will not grant resource actually. We will just tell the process, sorry, I cannot grant you resources right now because the system will go to a unsafe state. So wait, when time is fine, I will grant you resource. So operating system will tell the process like that. Now let us see how the banker's algorithm verifies whether the system is in a safe state. Consider we are using a vector called finish. So it is showing you the value false if the process hasn't completed execution, otherwise true. Initially, P0, P1, P2, P3 and P4 hasn't executed, so they are not complete yet. So finish of, if we call each index with variable I, we can say that finish of I is false for every index. Okay. Now in this banker's safety algorithm, we need another vector called work. It is actually a backup of available. That is the number of free resources in the system. So these two things are initially done. Finish, we will make a vector which has all the values false initially if all the processes are still waiting to get executed. And work, it tells you what is the current available resources. What are the resources which are currently free for allocation. Now what we do is, we will calculate the future need for each process. We know what is the maximum requirement of resource for each process. What is the current allocation to each process? Now we can calculate another value called need. It tells you what is the future need or future requirement of each process. So that will be calculated like maximum requirement minus current allocation. So let's calculate that value. Max matrix minus allocation matrix will give you future requirement. So we are trying to verify whether this system is safe or not. We are going to check whether all the processes P0, P1, P2, P3 and P4 are able to run in any order. So we have found the need matrix like max minus allocation. So we understand that P0 requires a 0 instance more, 0 instance or more for all the resource types. So that means P0 doesn't require more resources. It can now peacefully terminate and leave. Okay. Then P1, it needs 0 more instances of resource type A to complete. B, P1 needs 7 more instances of resource type B for completing execution. 5 more instances of resource type C and 0 more instances of resource type D. So If P1 gets all these resources together, P1 can complete execution and leave. When a process completes execution and leaves the system, the process will release the allocated resources. That means if a process leaves the system, this allocation of that process will add to the free resources. So that will be added to work. So let us see how we will proceed with this. We have already found the need matrix. The next step is we have to find out an order in which the processes will execute. If all the processes gets executed in some order, we can say that the system is in a safe state, otherwise unsafe. So we have the matrix need, which we found like max minus allocation. We have the finish vector. We have work, that is a backup of available, that tells you how many resource types, how many instance of each resource type is currently free in your system. So first thing we have to do is look at the need matrix. Look at the future need and find a process Pi such that the future need of the process is less than or equal to work. Future need of the process is less than or equal to current number of instances of resources free in the system. Then only the process can be allocated resources. So initially the algorithm will check whether there is such a process. So look at P0. P0 is requiring 0, 0, 0, 0. Yes, it is obviously less than 1520. We have one instance of resource type A, 5 instance of resource type B, 2 instance of resource type C, and 0 instance of resource type D presently free for allocation in the system. So obviously you can execute P0. P0 doesn't need anything. So P0 executes. When P0 execute, what happens? Allocation of P0 gets released. So what is the allocation of P0? You look here. This is allocation of P0. So these were the resources currently held by P0. They will be released and P0 terminates and leaves. So these resources will go to work. It will go to free resources. So we have to add 0, 0, 1, 2 with 1520. Now we are updating the number of free resources in the system, like work equal to 1520 plus allocation of P0, because allocation of P0 is now freed because P0 has completely executed and left. That will give you new value of free resources in the system 1532. Now 1 instance of A, 5 instance of B, 3 instance of C, 2 instance of D are free in the system and P0 has completed execution. When P0 completes execution, we will make that finish of P0 to true. Now again find a process such that need of process Pi less than or equal to work. Okay. Let's check with P1. P0 has now completed execution and left. Now P1 0750. Can P1 execute? What we have, the free resources in the system is 1532. Can P0 execute? No, because for B, can P1 execute? No, because for resource type B, P1 needs 7 instances, but we have just 5 instances now. And for resource type C, P1 needs 5 instances, but we have just 3 instances at present. So the operating system will tell P1 to wait. Then it checks with P2. Can P2 execute? Yes, because Requirement of P2 is 1002. Our availability is 1532. Yes, P2 can execute. P2 executes completely and leaves. What happens? Finish of P2 will become true. And allocation of P2 will add to this value. Add to work. So work equal to work plus allocation of P2. When P2 leaves the system after complete execution, all the resources held by P2 should be added to the free resources. So P2 executes and the current value of work is updated to 2886. That means 2 copy of resource type A, 8 copy of resource type B, 8 copy of resource type C and 6 copies of resource type D are currently free in your system. Now let us check the need for P3. Can P3 execute? Yes, because we have enough resources. P3 needs 0020. We have 2886. Yes, obviously P3 can execute. Now P3 executes. When P3 executes and completes, it terminates by releasing all the resources it was holding. And we will make finish of P3 to true. Then we will add allocation of P3 to work. So new value of work becomes 2886 plus 0632, that is 2 14 11 8. Now we will look again at the need matrix. Can P4 execute? Yes, P4 can execute. Because need of P4 is less than or equal to current value of work. So P4 executes. It executes completely because it got all the required resources. And it terminates by releasing the resources it was already holding. Now the value of work becomes work plus allocation of P4. And we will make finish of P4 to true. Again, the loop continues. We have to check whether P1 can execute. Yes, P1 can now execute because need of P1 is 0750. We have enough resources to grant now. We have 2, 14, 12, 12. Yes, we have. So we will let P1 to execute now. When P1 executes and leaves the system, it will release all the resources it was holding and the value of work becomes current value of work plus allocation of P4. That will become 3, 14, 12, 12. And we will write finish of P1 is equal to true. Now come to this vector. Come to finish vector. Check whether all the indices have the value true. Yes, all the indices have the value true. What does it mean? Yes, it means that all the processes at that time instant t has completed execution. Now you can confidently say that the system is safe because all the processes could execute in some order. The system is safe. Now we have found out the system is in a safe state because all the processes executed. And what was the order of execution? P0 executed, P2 executed, P3 executed, P4 executed, and P1 executed. So, the order of execution of processes in the safe state is known as safe sequence. And the safe sequence here is P0, P2, P3, P4 and P1. So that is the one phase of the Banker's algorithm. We have already learned how to check whether the given state is safe. Now, let us assume that the process P1 is asking a few more resources to the operating system. It is asking for 0420 of resource type A, B, C and D respectively. It asks the operating system, hello, I am process P1, I need 0 copy of resource type A, 4 copy of resource type B, 2 copies of resource type C, and 0 copy of resource type D. Can you grant these resources to me immediately? When the operating system gets such a question from P1, it thinks for a while. Can I grant it immediately? Oh no, I have to think. If I grant these resources immediately, will the system work peacefully or it will go to a deadlock? The operating system is thinking. Uh, I have to think. Then it is actually trying to avoid deadlock here. In the banker's algorithm, it is trying to avoid deadlock. So operating system is thinking like this. P1 is asking me for resource types A, B, C and D 0, 4, 2, 0 instances. Is he asking for resources higher than his maximum requirement? So the operating system will check through the banker's algorithm. It will check whether P1's request is legal. If this request is greater than its future need, it will say that, oh, your future requirement is calculated in the need matrix, but you are asking more than that. Your request is invalid. Sorry, go. Then, if the request is not invalid, the operating system will see whether there is currently enough available resources free to give. If there is not enough resources available, free resources are not enough at present, the operating system will right away tell to the process P1, you wait, I do not have enough free resources to give you. Now, assume that while process P1 is asking to the operating system for these resources and there are free resources at present, the operating system cannot grant it right away. It have to think. If I grant these resources right away, I will get a new state of the system. I will get a new snapshot. But will that be a safe state or not? If that will be a safe state, I can grant these requests. Otherwise, I will have to tell the process P1 to wait. So this is what the banker's resource allocation, resource request algorithm does. So assume that there are enough resources available in the system. There are enough free resources right now. The operating system will pretend like it is granting the resource request immediately. It is not actually granting, it is just pretending like it is granted. And it will get a new state, a new set of values for the need metrics, for the allocation metrics, for the available metrics. Max metrics will not change, okay. Using these values, it will again check whether that state is safe. If that state is also safe, then operating system will say, oh my god, the system will be safe. So I can grant these resources immediately, peacefully, no issues. Then only if the system will be in a safe state after granting the resources, the operating system will actually grant the resource to process P1. Let us see how this works. So, first we pretend like the new request is granted. So, we have to make a few changes to the snapshot. So, just to recollect the snapshot we have processes P0, P1, P2 and P3 and P4. We have 4 resource types A, B, C and D. We have k instances of each resource types. We have the value of current availability of free resources in the system. Okay, we have all those values. Now, assume that we are pretending like we have allocated the new request to resource request of resources to process P1. then you have to make a few changes. What are those changes? From where you are giving these resources? Yes, from the list of free resources. From available, or from work, we are giving these resources. So we have to reduce the request vector from available. So new value of available becomes available minus request of I. Then now request of I has been allocated to that process P1. So for P1 we have to make that change in the allocation matrix, isn't it? In the allocation matrix we have to add more values, add the more resources which are granted to P1. So allocation of P1 becomes allocation of P1 plus request of P1. Now we have to update the need matrix. What is the future need of P1? Future need of P1 will be reduced because P1 is already granted a request of 5. That much resources more are granted to P1. So the future need reduces, isn't it? So need of P1 is equal to need of P1 minus request of P1. Here P1 is asking for resources 0420. So request of I is 0420. And you have to make these changes. Available is equal to available minus allocate request of P1. Now allocation of P1, you have to make that change in the allocation matrix. Allocation plus request of P1. Need must be updated like need minus request of P1. So this was the previous snapshot. We have request of I P1. Request of P1 is 0420. Here I is P1. Process P1 is asking for these much resources 0420. So first the system will check whether these resources are available. 1520 is available. Okay, yes, it is available. So the system can think about giving resources right away. It is just pretending. It is just acting like it is giving resources, and it will foresee whether there will be a deadlock or not. The value of available is 1100 new value. So 0420 is given from previous value of available 1520 minus 0420. We will get 1100. That is the current value of available. These much resources are currently free in the system. Now go to the allocation matrix, and we have made a change here. We have allocated more resources to P1, so that change is added to allocation of P1. Now max matrix doesn't change. That is something the process tells the operating system once it is created. Okay. So we now have a new snapshot of the system. We have a new value of allocation matrix, new value of available vector, and the value max. So this was something we found when P1 requested for resources. The operating system have to think whether P1 should be given these resources right away or not. So let's proceed. Now P1 is granted resources. It is operating system is pretending to be granted the resources. Now there is a new state in front of us. We already know we have how to check whether this state is safe or not. We have already seen the banker's safety algorithm. We will run that safety algorithm here. On the new state, we will run the banker's safety algorithm. We will check whether new state is safe. So the available vector is this one. Finish vector, it is initialized to false for all the indices. Work is equal to available. It is the backup of available vector. It is equal to 1100. Now the need matrix. So this is the need matrix. In the need matrix, the need of P1 is reduced by request of I. Allocation of P1 is incremented by request of I. Now we will check whether these processes can execute in some order. We are going to check whether this state is safe. So go to the need matrix, check P0. What is the requirement of P0? It is 0000. Yes. It is obviously less than or equal to 1100. Yes, we can allocate. So P0 can execute and leave the system by releasing the resources it was holding. So P0 works and it completes execution by releasing the resources 0012 to the list of free resources in the system. So it will be added to work. Now we have to add work plus allocation of P0. So we got the new value of work and we will then write finish of P0 is true. Yes, P0 has completed execution and left. Now look at P1. Is the future need of P1 less than or equal to current available free resources? Yes. Yes. No. Because P1 needs 3 instances of resource type B. But do we have that much instance of resource type B free at present? No, we do not have. We have just one instant. It is a shortage. And for resource type C, P1 needs 3 instances. Can we grant resource type C to P1 now? No, we cannot grant. So, P1 will not be executing right away. It waits. Okay, P1 is waiting. Now go to P2. P2's need is 1002. So, yes, you can grant 1002 is less than or equal to 1112. P2 executes and it leaves the system by releasing the resources P2 was holding. Now, work will be updated to work plus allocation of P2. So, this is allocation of P2. We will add 1112 plus 1354 and we will make finish of P2 to true. Now go to the need matrix, check the next process. Next process is P3. Can P3 execute now? Yes, because 0020 is less than or equal to 2466. So it can execute. So P3 executes and it leaves the system by releasing the resources it was holding. So new value of work becomes work plus allocation of P3. And we will write finish of P3 to true. Then go to the need matrix again. Check whether P4 can execute. So P4 requires 0642. Do we have that much resources free now? Yes, we have. So we will execute P4 and P4 leaves by releasing all the resources it was holding. So these were the resources P4 was holding. Now we will make work equal to work plus allocation of P4. And we will write finish of P4 is 2. P4 has finished execution. Again, we will check whether P1 can now execute. P1 is waiting, isn't it? So when resources becomes free, P1 executes. So P1 executes. When P1 completes execution, it leaves by releasing all the resources it was holding. So new value of work becomes work plus allocation of P1. So it becomes 3, 14, 12, 12. And we will write finish of P1 is true. Now look at the finish vector. We have all the values true. What does it mean? Yes, it means that the new state is safe and all the processes have completed execution in an order. Any order, no problem. So the order here is P0, P2, P3, P4 and P1. That is the safe sequence. So what did we found now? What did we find now? We found that if the request of process P1 was granted, we got a new state and the new state is safe. We found through the banker's safety algorithm whether this state is safe. So now it is a relief to the operating system, no tensions. It can easily, confidently grant those resources to process P1. So if at the end any of the process was not executed if any of these values was not true. The system will be in an unsafe state, and then the operating system would have told P1 to wait. In this case, we have proved that the system, the new state, is also safe. If the resource is allocated to P1 right away, there will not be a deadlock in the new state. So, the operating system can peacefully grant the resources immediately to P1. So, P1 gets its requested resources immediately. So, this is about the banker's algorithm for deadlock avoidance. This algorithm is actually avoiding a deadlock situation. How does it avoid the deadlock situation? When a process requests for resources, it pretends that the resource is granted to that process, and it will check the new state is safe or not. If the new state is also safe, the operating system can confidently grant the resource to the process immediately. This is called the banker's deadlock avoidance algorithm. So that is the end of this lecture. Hope you understand. Thank you.